Alright folks, today is day 2 of graphing rational functions. You will need a graphing calculator and a straight edge for today. The first two problems on your class examples here are review from last time, because I'm going to want you to find the vertical asymptote and then x and y intercepts algebraically. Okay, so I want you to pause the video and see what you can remember from last time on 1 and 2. Alright, so hopefully you remember anytime you see a quadratic you want to try to factor. This is a difference of squares, x plus 2 and x minus 2. Vertical asymptotes come from the denominator. Because nothing cancels top and bottom, we actually have two asymptotes here, at positive 2 and at negative 2. Okay, remember those are the ones that make the denominator 0, so a positive 2 plugged in and a negative 2 plugged in both do that. X-intercept is found by plugging y equals 0, so I just have to set that thing equal to 0. When I multiply over the denominator, that goes away, and I'm left with x plus 1 equals 0. So my x value is negative 1. Since all of these rational functions look like fractions, you're always going to just have to set the numerator equal to 0 to find those x-intercepts. Y-intercept, the 0 goes in for x, and you can use the factored form or the original, but I actually recommend using the original equation because then we don't have to worry too much about operation. If you use the original, that looks like 0 plus 1 over 0 minus 4, so it's just 1 divided by negative 4. If you're trying to use the factored version, it would look like 0 plus 1 over 0 plus 2 times 0 minus 2. And so you have to remember that's 1 over 2 times negative 2, so it's just a little bit more steps there. Second one here, graphed, the equation actually just flip-flops what you saw before. So we only have one vertical asymptote this time at negative 1, but because there are two things on top, we have two x-intercepts when we set that equal to 0 at negative 2 and positive 2. The y-intercept, again, I recommend using the original, and the only thing we have left is negative 4 divided by 1, or negative 4 for that. Now, the reason I had you grab your graphing calculator for this is we're going to talk about how these equations that we just looked at are different from what we did last time. So last time, when we looked at a rational function, the numerator and the denominator matched. So if it was a line on the top, it was a line on the bottom. If it was a quadratic up top, it was a quadratic on the bottom. And we decided that to find the horizontal asymptote, we just divided the leading coefficients. These ones are different because the numerator and the denominator aren't the same value. So what we're going to do is take a look at their graphs and see if we can determine a pattern from the asymptotes that do show up. Okay, so what I want you to do for the first one, we'll go back to it, let's type it in our calculator and just sketch it with the asymptotes labeled. Okay, we won't worry about putting the intercepts on there because we're really just caring about what happens with that horizontal asymptote. So, in your y equals, in order to type this in, you do have to have grouping symbols around the numerator and the denominator. So, parenthesis first, then x plus 1, close it, then division, another grouping symbol, x squared minus 4. I'm going to start with just a Zoom 6 window, and hopefully that'll let us see what's happening. We already knew that there were two vertical asymptotes, at negative 2 and positive 2, and you can see those show up here. Okay, but what we're looking for is to see if there is a horizontal asymptote that's showing up. Okay, so what I want you to do is just pause the video while you draw on just x and y axis in the space to the right where you have some room, and then I want you to sketch what you see here. Our graph looks something like this. We had x equals negative 2 and x equals 2. There actually is a horizontal asymptote here. at y equals 0. Now, I do want to point out something here that's a little bit interesting, and I'll talk a little bit more detail about it later. We have an asymptote, but the asymptote is guiding the ends of the branches way on the left and way on the right. It's not saying anything about what's going on in the middle. So it's really important to note that horizontal asymptotes aren't restrictions like they are for vertical asymptotes. They're just saying what happens at the very end, or when x is towards positive infinity or x is towards negative infinity. So it can't actually cross over that asymptote at any time in the middle. Okay, let's do the same thing for the graph of the second one. Okay, let's type this in, our y equals, and see what's going on there. Again, we want to make sure that all of our terms in the numerator are wrapped in grouping symbols, and same thing goes for the denominator. Alright, this is a very strange graph. I'm going to actually start with what we know, and that's the vertical asymptote. Remember, it came from this denominator. It's at -1, and you can see that on the graph. And there's definitely not a horizontal asymptote because our branches aren't riding along a horizontal line, but they are actually guided by a line. So I know that this one is. The sides of this curve are hitting there, but also there's an asymptote going this way. And that's considered an oblique asymptote, and that's what that OA has been standing for that we crossed out last time. So let's go ahead and sketch this thing. I know that's happening, and it looks like I'm going through here a little bit, and I'm just going to sketch this really roughly. We'll talk about where the equation actually comes from when we get to a specific example. Okay, so right through here, and then the asymptotes guide my curve on both sides. You can see your other critical values that were over here on your graph. We said that the x-intercept was in two places, at -2 and +2, and there was a y-intercept at -4. You can see that as well. Okay, so the big idea here is the reason that we had these different types of asymptotes happen was because the numerator and the denominator didn't match. And the difference between number 1 and number 2 is where the bigger value is. Okay, so here, the quadratic is on top. And what that meant for us is that we had an oblique asymptote. Okay, the reason for that is if it's bigger on top, as I get larger and larger, it's going to keep going up and up and up towards this positive infinity, just like the line does. Okay, as I go left and left and left, it'll get smaller towards negative infinity. If I go back to my first graph, this equation was bigger on the bottom. Okay, if it's bigger on the bottom, as I go through here, if you look at the graph, as my number gets bigger and bigger, my fraction actually gets smaller and smaller. I'm going to explain this using one of our parent functions we're really familiar with, where it's bigger on the bottom. That's a hyperbola. So if you think about plugging in x values like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 10, 1 over 100, 1 over 1,000, as the x value gets larger and larger, the fraction gets smaller and smaller towards 0. That same pattern happens even if there's an x on top any time that the equation on the bottom has a larger power, because the bottom then would get bigger faster, meaning the fraction is smaller towards 0. So when it's bigger on the bottom, you're always going to have a horizontal asymptote at 0. And that's what we're going to see happen in our practice today. Okay, our first step in general for all of these problems is to talk about either a horizontal asymptote or an oblique. Now that we know that's kind of the difference between all of these and the other parts stay the same, let's start there. Okay, so horizontal or oblique. You'll have a horizontal asymptote if they're equal or if it's bigger on the bottom. you'll have an oblique asymptote only if it's bigger on top. Okay, so first up looks like quadratics on the bottom, and if it's bigger on the bottom, we have the fraction go to 0. So there is not an oblique asymptote. There will only be one or the other for all of these. From there, it's the same process as we have been doing. Okay, we want to factor anytime we see a quadratic so that we can solve some of these things algebraically. So on the top we just have a line, so we can leave that alone, but on the bottom we've got a quadratic, and since there are two terms here, we're looking at GCF, and an x can come out. Remember, if you see the same thing on top and bottom, you can cancel it out, but that leaves you with a hole. So I want you to put hole on the vertical asymptote line because it will affect our domain. Okay. Things that affect our domain, or restrictions, are values that cause the denominator to go to 0. So the reason this is a restriction is because it was in the denominator, and the number 3 would make that go to 0. Okay, so you always switch the sign. Right? Then we want to rewrite what's left. Because we canceled out the top, we're just having a 1 there, and then there's an x on the bottom. So then, to find the y value, all we have to do is take this x value and plug it in right here, so that would look like 1 over 3, or 1/3. The vertical asymptote deals with the bottom. We had an x left, and it's whatever makes that bottom 0, and that would be 0 itself. Okay, another way to think about this is this one just happened to reduce to something we're pretty familiar with. Our parent function of the hyperbola has an asymptote at 0 and 0, and that matched up for us here. Alright, on to x-intercept and y-intercept. Hopefully you can see that from the graph as well. Based on our parent function, there shouldn't be either of those, but I'll show you how with the algebra. X-intercept says y is 0, so we're taking this equation and saying 0 equals 1 over x, and when we multiply that over, we get 0 equals 1. That's not true, so there are no x-intercepts. Y-intercept, we're putting a 0 in first for x, so that looks like 1 over 0, and I can't divide by 0, so that doesn't work either. Okay, I told you domain uses all these things up here. We only care about x values, so negative infinity, 0 is the lower one. Always pick up where you left off, so we're starting right back at 0, and the other x value is 3. Alright, a big part of the practice today is getting better about choosing a nice window for our graph. Okay, what we want to do is start with the x and y axis and figure out where a good place for those is. Okay, looking at your asymptotes, if they're close to 0, you want to keep your x and your y axis in the middle. If they're not close to 0, we'll shift them some direction to make them kind of closer to the middle for us. Because these are right at 0, that's good news for us. We'll start by just drawing on our x-axis and our y-axis directly through the middle. The next question we're going to ask ourselves is an appropriate scale. Because you know that this graph is just a hyperbola, all we really have to do is make sure that these points are going to show up on our graph. So the only point that we have is 3 1/3. That means I would be okay to count by ones here and say 5, 5, -5, -5, because all the numbers that I'm going to put on my graph fall in that range. Okay? It would not be wrong to go bigger if you wanted to go 10 by 10. Okay, but here, since we don't have a lot going on, this is okay. You want to label your asymptotes here even though they're on the axis. You don't necessarily have to dash them because we wouldn't be able to see it much, but you do want to label them. From there we can put on our 1 point. It was 3 1/3. And it looks like we're good to go ahead and connect this branch. Even if we didn't know what the shape was going to look like, our asymptote and our point tells us. We always start at the asymptote, go through the point, leaving that hole empty, and then ending at your other asymptote. Then, say we didn't know what this was, Our next job is to talk about the second branch. It has to be either to the side or below here, because we can't go below to fail the VLT. So all we have to do is just pick an x value that's over on the left here and plug it in our equation, just like we did with the y-intercept. Okay. So an x value to the left may be -1. You can choose -1, -2, -3, your choice, and we're going to plug it in. So my equation was 1 over x. I'm going to plug in x equals -1. That would look like 1 over -1 from that equation, which means my point is -1, -1, and I'll plot that. Again, start at the asymptote, go through the point, and end at the asymptote. Okay, next up, again, you're going to decide the horizontal or oblique asymptote first, based on are they equal, bigger on top, or bigger on bottom. Okay, this one has the equation on top quadratic, okay, which means we're going to have an oblique asymptote, not a horizontal. Okay, and so I need to show you how to tackle the oblique asymptote. The first thing you're actually going to do is try to factor, because when we talk about an oblique asymptote, it just tells us what this gets close to as you divide it. Okay, so one way to simplify when division is just factoring to see if something cancels. If it doesn't cancel, that's when the oblique asymptote actually shows up. Okay, so starting out, we'll go ahead and factor the top and the bottom. Okay, so try to think of the factors of 3 that add to be -2. Okay, this one actually doesn't work. If we think about the factors of 3, they have to be 1 and 3 or -1, -3. Okay, that's the only way to multiply to be a positive value. Either way, I get a 4 or a -4, which is not -2. What that means is this thing's not factorable. And if it's not factorable, we can only use this equation to go answer all those questions. Okay? It will cause some potential difficulty here in a little bit, but for right now we're going to focus on the oblique asymptote. Okay? What we're going to do is divide these instead of by factoring, since we couldn't, by synthetic division. Okay, this is something you talked about briefly in Algebra 2, and we'll talk about it more later this year. But synthetic division takes the coefficients of this and divides it by the 0 of the denominator. So how we'll set it up is start out with the coefficients from the numerator. So the x squared has a coefficient of 1, the single x has a coefficient of -2, and the constant has a coefficient of 3. If anything is missing, you have to fill it in with 0. So go in order: squared term, single x, and constant. Then you're going to draw an upside down box for a division, and on the outside we divide by the 0. So that is the number that makes the denominator go to 0, just like our vertical asymptote. So switch the sign of what you see. So we'll put a +1 on the outside. Then the operations we want to remember are on the inside we'll add, and on the outside we'll multiply. So first step, just drag down your 1, and then we do what it says. So outside it's 1 times 1 is 1. We'll go inside the box from there. Then we're supposed to add on the inside, so -2 plus 1 is -1. Outside again we multiply, so 1 times -1, -1, and straight down we have a 2. This 2 I want you to put a box around. This is the remainder. The one right next to it is the constant, and then the one next to that is the single x. It's the slope of our line. So the remainder here, while you normally wrote it like this, just remainder 2, it actually means that we have 2 out of that x minus 1 left over. And because this whole idea is talking about end behavior, as this gets really large, like a lot of zeros, we're saying 2 divided by a bunch of 9s, which is a really small number. Okay, just like what we were talking about with that bigger on bottom, it goes to 0. This whole remainder, in the end, where x is increasingly large towards infinity, goes away. It's practically 0. So we'll always cross out the remainder when we do synthetic division. But this represents the equation of our oblique asymptote. It's the equation of the line. We write it as y equals, I said this was the slope, so 1x or just x, and our constant was -1. And that's it. Now we can go back to the other problems here. Vertical asymptote, remember, comes from the denominator. X is 1. The x-intercepts is where I said we would create a little bit of difficulty because that thing wasn't factorable. Remember that an x-intercept is when y is 0, and that's setting the numerator equal to 0. Well, when a quadratic is not factorable, that means the zeros, or the solutions, are not rational. So the only other option is they're irrational or they're imaginary. So we have to go to a different method to solve. So instead of factoring, we're going to try quadratic formula. So quadratic formula opposite of b would look like positive 2 plus or minus b squared would look like 4 minus 4 times a is 1 and c is 3. So I'm just using the a, b, and c from the numerator here. Then on the bottom, 2 times a is 2, and we simplify. Now, I'm not going to work very hard here because I know that 4 minus 12 is a negative number, and when you take the square root of a negative number, it's imaginary. So imaginary solutions don't show up on the graph. You will never have to graph those. So as soon as you see that there's a negative underneath that square root symbol, you're done. Okay, cross out that x-intercept. Y-intercept, plugging 0 in for x. So going through here again, the original is nicer, I think, because we're just left with 3 divided by -1, which is -3. Finally, domain is everything but our asymptote or holes, and we don't have any holes here, so -infinity to +1, union 1 to infinity. Alright. Again, we want to decide x and y axis if we're keeping them in the middle or moving them first. To decide, you look at your asymptotes and see if they're close to 0. If they're close to 0, you leave it. If it's not close to 0, you move it. So this one's fine. When we're looking at an oblique, when I say close to 0, you want to see if this y-intercept is close to 0. That will tell you whether you need to shift your equation or not. Both of those are very close to 0. So we're going to start with through the middle, both left and right and up and down. Okay, what I want you to do with oblique asymptotes is always count by 2s. Okay, because they look a little bit strange on the graph, we don't want to cut out too much of our graph where one of our curves would be way on the edge. Okay, so always start bigger and count by 2s for this, which would mean 10s all around for us. Okay, even though a -3 is the biggest thing I see, it just gives us more room to work with. Okay, we're going to start with graphing what we know, the +1 for the vertical asymptote. Because we're counting by 2s, you got to watch your scale. We'll plot the oblique asymptote just like we would a traditional line. You're going to start at the y-intercept as -1 and plot a point. And from there, we're just going to count the slope. Okay, so up 1, right 1, up 1, right 1, up 1, right 1, all the way through. Now, if you do a good job of counting by the same number on your x-axis as you do your y-axis, so we counted by 2s on both of these, then graphing this is going to be made a lot easier, because you wouldn't necessarily have to go up 1, right 1. You could go up a whole box over a whole box, up a whole box over a whole box, because you're counting by that same number each time, and the fraction would reduce to the same. I'll talk a little bit more on that for the next one. Okay, but when you connect those, just do so with a dashed line since it is an asymptote. But we're going to label it to the side just like we have been on the other one. So y equals x minus 1 there. From there, we just have to plot what we have given to us, and that was just this y-intercept at 0, -3. Now, this is a weird little triangle shape, but these asymptotes guide us the same way the other ones do. We always want to start near the asymptote, go through the point, and then end near the other one in that little quadrant that we have. So it kind of makes this parabola-looking shape. Alright, then it looks like we're missing something on this side because we're out of points to plot. So we just have to pick something to the right of 1 to plug in. Because there is not a factored form, we just have to plug this into the original. And I'm going to pick 2 and plug it in right here. So for x equals 2, that would look like 2 squared is 4, minus 2 times 2 is 4 again, plus 3, and then down below, 2 minus 1 is 1. So 4's cancel out, looks like I'm left with 3. So my ordered pair is 2, 3. And I can start at that asymptote, go through the point, and along the asymptote, looking like another parabola-like shape. Couple more here. We've got another example where it's bigger on top. Okay, so bigger on top for us, remember, means oblique, which means it can't be this. We do want to try to factor first because that's the easiest way to divide stuff. We can factor this one, x plus 2 and x plus 5. Okay, but nothing cancels, so for the oblique asymptote, we're going to use synthetic division. Remember, for synthetic division, we're going to go to our numerator and write down all the coefficients in order. If anything's missing, remember, put a 0 in there for it. On the outside, our divisor is just the opposite sign of what you see below. So we have a plus 1, that'll be negative 1 for us. Okay, drag down the 1 first, then outside multiply, inside add. So negative 1, positive 6, negative 6, remainder of 4. That remainder doesn't matter to us, but this 6 is our constant, and this 1 is the slope of our line. It goes with x. So y equals 1x, or just x, plus 6. Okay, what I want you to do now is pause the video and fill out all of the other things with algebra, and then we'll graph it together. Vertical asymptote is at negative 1. X-intercept we have 2 of because there are 2 numbers up top. Negative 2 and negative 5 would work for us. Y-intercept is 0, 10. Again, I like to use the original, and it's just what's left, the 10 divided by 1. Domain, negative infinity to negative 1. Union, negative 1 to infinity. We're going to start by deciding about our x and y axis. Okay, so we'll start with this number. Negative 1 is pretty close to 0, so it's okay for us to put our y-axis right in the middle. Okay, but the number 6 is not very close to 1. Okay, if we think about this line, and I'm just going to sketch this below for kind of a visual here. If we think about this line, 6 is way up here, and then my graph would be up here, line is here. So I really need to move my whole graph down some so that this little intersection is more towards the middle of my graph. So that's the whole idea. Because 6 is higher than 0, we need to move the x-axis down. So I'm going to go ahead and put it pretty close to the bottom here. A little crooked there. And in fact, if you notice that there are no negative y values, you can put it even closer to the bottom, maybe at the edge there. But I told you last time, when you're doing oblique asymptotes, always count by 2's. So from wherever you put your x and y axis, you want to start at 0 and then just count by 2's. So 2, 4, 6, 8, 10 to the right, and 10 to the left. And then up we went 2, 4, 6, 8, 10, 12, 14, 16 looks like. And then 2, 4, negative 4. Then we can go ahead and start graphing some of these things. The first thing that we had was the x equals -1. So vertical asymptote, dashed line at -1. Alright, then we're going to graph our other asymptote using the y-intercept and the slope. So 2, 4, 6 is right about here. And then our slope is up 1, right 1. We're counting by 2's, but instead of going up 1, right 1, we can go up 2, right 2, just counting by those blocks. And that's why I had you keep it where whatever you count by on x, you also count by on y. That way, we can graph this just a little bit more quickly. Then we can connect those. Okay, and it looks like, for the most part, this is pretty dang close to the middle. It's not perfect, but it's not bad either. Then plotting our points, we have -2, 0, -5, 0, and we can go ahead and connect that curve because there's 2 points. And then our last one is 0, 10. And we lucked out on this one because we had all of our points in different places so that we could actually do both curves without picking our own. So that's kind of nice. Last graph, okay, we're bigger on the bottom, which means we don't have an oblique asymptote. It's a horizontal one, and it's at 0. Once again, I want you to pause the video and do the algebra for that one. Okay? If you feel comfortable enough, try graphing it as well, and then I'll go through on how to pick an appropriate window and graph some of these points that show up. Okay? But try it on your own to see if you can figure some of that out. Factoring here, we've got x plus 4 and x minus 3, which means we have 2 vertical asymptotes because nothing crossed out at -4 and +3. We don't have any x-intercepts, okay, because when you set this equal to 0 and multiply that over, it says -2 equals 0, and that's not true. This was kind of like the hyperbola that we saw on the front side. When you don't have x in your numerator, there won't be any x-intercepts. Okay, so that's one way to remember as well. Y-intercept, you're plugging in 0. We do have one of those because -2 divided by -12 is 1/6. Domain, I'm stopping at 2 spots here. -4, and then from -4 we go to 3, and then 3 to infinity. Okay. The idea for these types of graphs, when you have 2 vertical asymptotes, is you kind of want to center them around 0. Because we have one positive and one negative, and they're close to the same value, they're only 1 away from each other, we can go ahead and start with the y-axis in the middle for this one. We just want to make sure we count by something large enough so that my my vertical asymptotes show up more in the middle versus way over to the left or way over to the right. So we got to watch our scale. But then, because our horizontal asymptote is at 0, it's good to put right in the middle of that x-axis. Okay. If I counted by 1's here, -4 would be way on the edge, so that's no good for me. So let's count by 2's. So +10, -10, and a lot of times if I can, I'll keep it square. It would probably be okay to count by 1's for the y's because we only have really a 1/6 there, but because we only have 1 point, that tells me we're going to have to plug in some points, and if anytime we're plugging in something, we don't necessarily know if it's going to be larger than 5 or not, so it's good to have some extra space in case something goes wrong there. Starting with our asymptotes like we have been, -4, +3, Horizontal one is at 0. You don't have to dash it. You do have to label it. And I know that my y-intercept is at 0, 1, 6. So there's that. Now, we learned that when we have two vertical asymptotes, a lot of times these branches over here are going to be opposite of what's happening in the middle, or maybe one's down here, one's up here, and there's like a snake shape in the middle. The middle can either be that snake shape, or it can be a parabola. So we've got a lot of different options here, but because this point is where it is, we actually know more than you think, because of what you see on the x-intercept. It says that we don't have any x-intercepts, which means as I draw my curve here, it cannot come below. It can't cross over that. And because of that, using the asymptotes, there's only one option. I have to start at this asymptote since I can't cross over. I know I have to go through the point, and again, I can't cross over, so it has to go back up after that. Okay, so 0, 1, 6 tells us exactly what's going on there. On the other side, I have no idea if it's above or below for these, so I need to plug in some points to decide. Okay, so you can use either equation, whichever you want, the factored version or the original, and I'll show you both for either side here. So, let's pick a negative value. Negative 5 looks good. So if we're using the original, that would look like negative 2, and then negative 5 squared is 25, then plus a negative 5, and then minus 12. So here, on top, I've got a negative 2, and on the bottom, I've got 20 for the first part, minus 12 is 8. So that simplifies to a negative 1/4, and I can plot that point. The x value is negative 5. Negative 1/4 is really close to that axis, and I can label that. Sometimes it's nicer to use the factored form because sometimes some of these numbers get pretty big with the original, so I'll show you that for this next one. Picking an x value to the right of 3, 4 will be good. And so the factored version, still negative 2 on the top, but I'm just going to fill in these factors and simplify. So first step would be 4 plus 4 is 8. Second up, 4 minus 3 is 1. And so that looks like negative 2 over 8 times 1 is 8, which is negative 1/4 as well. Okay, so original or factored, your choice. So 4 is here, negative 1/4 is here. Drawing my curve and labeling the point. That's really the ugliest it gets in terms of graphs when you have those two vertical asymptotes. If you ever have trouble, especially with like the middle of deciding what should happen with that, please feel free to come see me. Worst case scenario, you can plug in some extra points like negative 2 and see what it comes out to be to kind of give you a little bit more points to be able to graph that. Okay, but when you're doing your homework, if you have any questions, please feel free to come see me.